A student is walking across a slope of broken volcanic rock in eastern Africa, scanning the ground the way he has scanned it 100 times before. Something pale is sitting half buried in the dirt. It is not a rock. Half a jaw, 5 teeth still locked in their sockets, and within a year, a number attached to that jaw will force paleoanthropologists to rewrite the opening chapter of the human story. Somewhere else in the same story, a fossil that was supposed to answer everything will instead raise the one question nobody had a good answer for. And by the end of this, you will understand why a single broken bone, half of one side of one jaw, was enough to push the origin of our own genus back by 400,000 years. Keep that number in your head. It matters more than it sounds like it should. This is not fringe speculation, and it is not a documentary built on guesswork. The fossil in question is catalogued as LD 351, recovered from the Ledi-Gararu research area in Ethiopia's Afar regional state. The discovery was made in January 2013 by Chalitu Seyum, an Ethiopian graduate student working with an international research team, and the findings were published in March 2015 in the journal Science, one of the most rigorously peer-reviewed publications in the world. The lead authors were Brian Vilmore, a paleoanthropologist then at the University of Nevada, Las Vegas, and William Kimball, director of the Institute of Human Origins at Arizona State University. A companion paper in the same issue, led by geologist Aaron DiMaggio of Penn State University, handled the dating. 2 separate teams, 2 separate methods, 1 conclusion. That is not how pseudoscience works. That is how real science checks its own homework before it lets a claim near the public. Here's the part that needs an analogy before it needs a number, because the number by itself will not mean anything yet. Imagine trying to read a book where 200 consecutive pages have been torn out, and all you have left is a fragment from somewhere near the missing section. That is roughly the situation paleoanthropologists faced for decades, with the window between 2 and 3 million. Years ago in eastern Africa, fossils from before 3 million years ago exist. Fossils from after 2 million years ago exist. But the stretch in between, the exact stretch where scientists believe our genus, Homo, split off from its more ape-like ancestors, was almost empty. Now, for the one number in this story that actually deserves 2 comparisons stacked together, because your brain needs both to feel the scale of it. LD 350-1 is dated to between 2.8 and 2.75 million years old. Picture the entire recorded span of human civilization, every pyramid, every written language, every empire that ever rose and fell, compressed into roughly the last 5,000 years. This jaw predates all of that by more than 500 times over. Now picture it a different way. If the current age of the universe were shrunk down to a single calendar year, this jawbone would belong to a moment that happened only a few hours before you started reading this sentence, geologically speaking, on a human evolutionary timescale where 3 million years is barely a blink. It is old in a way that resists intuition, and that is exactly why the fossil matters as much as it does. Before this discovery, the earliest fossil that could be confidently assigned to the genus Homo was dated to roughly 2.3 to 2.4 million years ago. Everything older than that had been classified as Australopithecus, the more primitive, smaller-brained genus made famous by the fossil known as Lucy, discovered in 1974 at Hadar, a site just 30 kilometers from where the new jaw would eventually surface. For 40 years, the transition between Australopithecus and Homo sat in a kind of scientific fog. Researchers knew it had to have happened somewhere in that missing window, but nobody had the physical evidence to say when or what the transitional individual might have actually looked like. LD 351 landed directly inside that fog and, for the first time, gave scientists something to hold on to. Now here's the part that connects the discovery to the mystery it was solving. The Ledi-Gararu mandible preserves the left side of a lower jaw, along with 5 teeth still in place. When Kimball and Vilmore's team examined it closely, they found something almost unsettling in how it straddled 2 different worlds. The overall shape of the jaw retained primitive, sloped features reminiscent of Australopithecus, but the teeth told a different story entirely. The molars were slim and proportionate rather than large and blocky. The premolars were symmetrical. The whole tooth row had an evenly balanced, streamlined quality that researchers associate with later Homo species, not their more robust ancestors. Kimball described it as showing a genuinely intermediate condition, a fossil caught mid-transition, neither fully Australopithecus nor fully modern Homo, but something moving deliberately between the two. That is not a comfortable finding for scientists who like their categories clean. It is, however, exactly what an evolutionary transition is supposed to look like when you are lucky enough to catch it in the act. 200,000 years. That is roughly the gap between the last known appearance of Australopithecus afarensis, Lucy's species, in the fossil record around Hadar, and the age of this jaw at Ledi-Gararu, just a short distance away. 200,000 years is not a small gap on a human timescale, but on an evolutionary one, for a lineage split of this magnitude, it is almost uncomfortably tight, which is exactly why the team did not stop at describing the bone. A single fossil, no matter how well preserved, is one data point. Science does not build conclusions on one data point alone. This is where the second team enters the story to check whether the bone was even telling the truth about its own age. That confirmation came from Erin DiMaggio and her colleagues at Penn State, using a technique called argon-argon radiometric dating applied to layers of volcanic ash found directly above and below the sediment that held the fossil. Volcanic ash contains crystals that trap radioactive argon gas the moment they cool from molten rock, and that gas decays at a fixed, well-understood rate over time. By measuring how much has decayed, geologists can date the ash layer itself with remarkable precision, and by extension, date anything found sandwiched between two dated layers. DiMaggio's team ran multiple independent dating methods on the site, and every one of them converged on the same answer: 2.8 to 2.75 million years old. In her own words, paraphrased from the published research, the team was confident in the age of the fossil precisely because several unrelated dating techniques all pointed to the same window. That is the triangulation that separates a real scientific finding from a lucky guess. One team examines the bone, a completely separate team, using completely different tools, independently confirms when it was buried. When both lines of evidence land in the same place, that is when a claim earns the right to rewrite a textbook. If you have made it this far, you already have the shape of the whole story. A jaw caught between two species, a date confirmed twice over by independent teams, and a 400,000-year jump in how far back our genus can be traced. If any part of that has surprised you already, this is a good moment to hit, and stay with it. Because the part that comes next is where the story stops being about one bone and starts being about the world that bone was living in. In the next part of this, we go straight into the environment itself, because a fossil never tells its whole story in isolation. Bones do not explain themselves. They need context, and the context for Ledigararu came from an unexpected source, not the hominin fossils, but the animals found buried alongside them. A separate research effort led by Kay Reed, also of Arizona State University's Institute of Human Origins, examined stable isotopes preserved in the teeth of ancient herbivores recovered from the same sediment layers. Isotopes are essentially chemical fingerprints left behind by diet. Animals that graze on grass leave a different isotopic signature in their teeth than animals that browse on leaves and shrubs. By reading those signatures across dozens of fossil animals from the site, Reed's team reconstructed what the landscape actually looked like nearly 2.8 million years ago, and the picture that emerged was stark. Almost every animal found alongside the early Homo jaw had a diet dominated by grass, indicating an open, arid, and grassland-dominated environment, a significant shift from the denser, more wooded habitats associated with earlier Australopithecus sites nearby. Here's where it gets genuinely interesting, and because this is not just a detail about ancient weather patterns. Some researchers have proposed that a broader shift toward a drier, more variable African climate around this same period may have acted as a kind of evolutionary pressure cooker, favoring traits like dietary flexibility, tool use, and eventually larger brains, all hallmarks of the genus that would go on to become us. Reed herself has been careful, on the record, not to overstate this connection. It is one thing to observe that the environment changed at roughly the same time Homo appears in the fossil record. It is another thing entirely to prove that the environmental shift caused the evolutionary one. Correlation sitting next to a landmark fossil is tempting. Responsible scientists resist turning it into proof before the evidence earns that word. That restraint matters, because it sets up the second major piece of this puzzle, one that complicated the tidy narrative almost as soon as the Ledigararu jaw made headlines. Just 2 years after the science papers were published, researchers led by Fred Spoor at University College London re-examined a different, previously known specimen, a partial skull found decades earlier and nicknamed informally after the site where an even earlier hominin skeleton had been located. That reconstruction, using digital imaging and CT scanning techniques rather than direct physical assembly, revealed a brain case larger than expected for a fossil of its age, alongside hand and finger bones that suggested an individual capable of grasping and using tools. On the surface, this looked like exactly the kind of confirming evidence that should have neatly slotted in after the Ledigararu jaw, completing a clean evolutionary staircase from Australopithecus to early Homo to more advanced early Homo. Instead, it complicated things. Spoor noted publicly that the specimen appeared, in his words paraphrased from his own comments, more evolved than its age should have, aloud, making it an unlikely direct ancestor for the very lineage it seemed to represent. The lady jaw's own primitive features made it a better candidate for that ancestral role, but researchers, including Kimball himself, were careful not to assign LD 351 to a specific named species, and deliberately avoided placing it neatly into any single confirmed lineage. It is, after all, one specimen, half of one jaw, and paleoanthropology has been burned before by moving too fast on too little bone. Let's pause here and pull the last few minutes back together in one breath, because a lot has been thrown at you. A student finds half a jaw in Ethiopia in 2013. Two independent teams, one studying the bone itself and one dating the rock around it, confirm it is between 2.8 and 2.75 million years old, pushing the known origin of our genus back 400,000 years earlier than anything previously confirmed. A third team, studying the diet of ancient animals nearby, reveals the fossil belonged to a world that had recently turned dry and open, a landscape under environmental pressure. And a fourth line of research, examining a completely separate skull, complicates rather than completes the picture, refusing to hand paleoanthropologists the simple, single-file evolutionary ladder that popular imagination often expects. That refusal, that mess, that unresolved tension between specimens is not a failure of the science. It is what real, honest, ongoing science actually looks like while it is still happening, rather than after museums have smoothed it into a clean diagram on a wall. Now, to be clear about something important, because this is the point in the story where the temptation to overreach is strongest, and where honest science has to slow down and resist it. LD 351 is a single mandible. It is not a complete skeleton. It has not yielded DNA, and given its age, nearly 2.8 million years, in a hot equatorial climate that is punishing to organic preservation, it almost certainly never will. Ancient DNA has a shelf life, and even in the most extraordinary preservation conditions on Earth, cold and dry environments, usable genetic material rarely survives much beyond 1 million years, with the oldest genomes ever recovered from permafrost-preserved specimens in far colder climates, still falling well short of 2 million years old. Nobody working on this fossil is claiming they sequenced its genome, because nobody did, and nobody could have. What researchers have is morphology, the physical shape of the bone and teeth, compared carefully against known Australopithecus and Homo specimens, and radiometric dating of the surrounding geology, which is a completely different, and in this case, more reliable line of evidence than DNA ever could have been at this depth of time. It is also worth being direct about what this fossil does not settle. It does not prove which specific Homo species it belonged to. Fillmore and Kimball's team deliberately avoided assigning it to Homo habilis, Homo rudolfensis, or any other named species, because the fossil is too fragmentary, and the surrounding fossil record from that exact window is still too thin to make that call responsibly. What it establishes is a genus-level marker, a confirmed presence of Homo-like anatomy at a confirmed date, not a confirmed species, and not a confirmed direct lineage running in an unbroken line to you. Population-level and genus-level evidence is powerful, and it is real, but it is a different kind of claim than an individual-level identification, and the distinction is one this field takes seriously, even when headlines sometimes blur it. It helps to understand why a jawbone, of all things, carries this much weight in paleoanthropology. Because to someone outside the field, it might seem like an odd place to hang such a large claim. Teeth and jaws survive better than almost any other part of a skeleton. Enamel is the hardest substance the body produces, harder than bone, which means that in the punishing conditions of fossilization, teeth and the jaw that holds them often outlast skulls, hands, and hips by a wide margin. That is not a coincidence of this one site. It is the reason so much of what we know about early hominins comes from exactly this kind of fragment. A jaw is not a consolation prize when a full skeleton is unavailable. In practice, it is often the single richest source of comparative information a paleoanthropologist can hope to find, because tooth shape, tooth proportions, and the geometry of the jaw itself change in predictable, trackable ways as one hominin species gives way to another. That is precisely what let Kimball's team read so much meaning into 5 teeth and half a mandible. They were not guessing. They were comparing precise measurements against a well-documented library of known specimens spanning millions of years, and the numbers themselves pointed toward a transitional identity before anyone offered an interpretation. There is also the matter of what has and has not happened since 2015. The Lidai Jararu project, still directed in part through Arizona State University's Institute of Human Origins, has continued excavating the site in the years since, specifically hoping to recover additional hominin material that could either confirm or challenge LD 351's placement. As of the most recent published work from the team, no second comparably diagnostic Homo specimen from that exact narrow window, 2.8 to 2.75 million years ago, has been recovered to definitively settle the species question. That is not a failure. That is the field being honest about the limits of a fossil record that remains, even now, frustratingly thin across exactly the years that matter most for understanding where we came from. Kay Reed herself has said publicly in comments, paraphrased from her own statements, that the aridity signal at the site is clear, but that it remains too early to say with confidence that climate change alone drove the origin of Homo, and that more fossils are needed before that claim can be made responsibly. That is what intellectual honesty sounds like, from inside an active excavation, not a closed case. So where does that leave the story that started with a student walking across a slope of broken volcanic rock in the Afar region of Ethiopia? It leaves it exactly where good science usually lands. Not with a tidy bow, but with a sharper, better evidenced question. Before 2013, the earliest confirmed trace of our genus sat at roughly 2.3 million years, wrapped in a fog that ran backward for hundreds of thousands of years with almost nothing to fill it. Now there's a jaw, half of one side, 5 teeth still in their sockets, sitting at the edge of that fog at 2.8 million years, close enough to Lucy's own lineage to blur the line between where Australopithecus ends and where we begin. It does not hand us a clean family tree. It hands us something more honest than that, proof that the line was never as clean as the diagrams made it look, and that somewhere in that missing window between 2 and 3 million years ago, something in a small population of primates in eastern Africa started becoming us, slowly, unevenly, without knowing it was making history. It is worth remembering, too, how ordinary the moment of discovery actually was. Chalachu Seyum was not sweeping a brush across a carefully marked excavation square when he found LD 351. He was surveying, walking a slope that field teams had crossed, many times before, doing the unglamorous, repetitive work that most fossil hunting actually consists of. Villemori later described the find, in comments paraphrased from his own public remarks, as something the team had been searching for deliberately, and then simply happened upon by chance in the right place at the right moment. That combination, years of deliberate, funded, methodical searching colliding with a single moment of luck, is how most transformative fossils actually enter the record. It is rarely a dramatic unearthing. It is usually a tired researcher glancing down at exactly the right patch of eroded rock on an otherwise unremarkable afternoon. Maybe that is the part worth sitting with longest. Every fossil like this one is a reminder that the story of our origin is not a straight staircase, climbing neatly upward toward the present. It is a scattered handful of broken bones, half buried in ash and rock, waiting up to 2.8 million years for someone to notice they were never just rocks at all. Tell us in the comments which part of this stayed with you more, the 400,000-year jump the jaw forced onto the timeline, or the fact that scientists still, honestly, cannot tell you exactly which species it belonged to.